Welcome everyone. So since last week we discussed inverse functions and exponential functions, it only makes sense that this week we discuss logarithmic functions. See, logarithmic functions are the inverse to exponential functions. So here are our objectives. It's kind of long because we were doing 2 sections today instead of just one, both 5.3 and 5.4. So a logarithmic function are, like I said, inverses of exponential functions. Here you can see we have something like y equals log base a of x, which is equivalent to writing that a to the y equals x. So if you're given something like this, which naturally comes out whenever we do inverses, and you want to be able to solve for y, logarithms allow us to do that. In general, you want x to be positive, and a is also going to be positive. A cannot be 1 either. And as I spoke it out before, we say the logarithm base a of x to read out this line up here. So in general, when dealing with these, it's helpful to remember this part is our base down here. It equals our exponent, which goes up here. And then the thing in parentheses is the thing on the right-hand side over here. So it's very much about placement, but as long as you can remember base A, which naturally falls base A in both locations, and you remember y, so the other side of the equals of a logarithm, is our exponent, you can always go back and forth between the two of these. So just to show you what it kind of looks like, if we have the function y equals 2 to the x, then x equals 2 to the y, well, that's our function y equals log base 2 of x. And you can see how it's actually reflected over the line y equals x as we would expect. So let's get some practice with each of these. Each of these should be doable by hand, and then I'll show you how you can actually type them into your calculator afterwards. So we have log base 2 of 8. That essentially tells me my base is 2. We're looking for what exponent, and then this equals 8. So we always take what we're taking the log of and set it on the right-hand side, and we always take the base to be the base that's raised to an exponent. Now looking at it this way, we say 2 to the what power gives me 8? Well, 2 to the third power equals 8. Therefore, log base 2 of 8 is 3. Now, don't think of it as log times 8 or anything else. It is truly a function we're applying to the number 8. Now, anytime that you don't see a base written, but it's written log, you want to assume it's base 10. That's true for your calculator as well. So if we take base 10, and we know it's 10 to something, gives us 1,000. There's our equivalent question. And so we know our question mark then equals 3 again, since 10 to the third is what gives us 1,000. Now on to the next one. Our base is 5. 5 to the what equals 125. Well, 5 times 5 is 25, times 5 again is 3, so we have another log equivalent to 3. Again, I could write log base 5 of 125 equals 3. It's all about pulling what was in that exponent. And let's go back. I want to make sure I write it down for the line above, log of 1,000. We also got 3. It's all about what exponent brought us there. Now this next one's definitely a little bit different, because it's 2 to the what equals 1 over 16. Well, it might be helpful to remember 1 over 16 is 1 over 2 to the 4, which of course is 2 to the negative 4. Therefore, our log base 2 of 1 over 16, well, that's the exponent, negative 4. Again, looking here, 2 to the what gave me 1 over 16? Well, minus 4. 2 to the minus 4 gave me 1 over 16. Now let's move on to the next one. My base here is 6, so 6 to the something equals 1. And here, hopefully you might be digging deep here, but you remember with our exponent rules, anything to the 0 power gives us 1. So that tells me this question mark equals 0. In other words, I could say log base 6 of 1 equals 0. Again, solving for the exponent. Lastly, we have our base is 5. 5 to the question mark equals 5. Well, of course, 5 to the first power is what gives us 5. So log base 5 of 5, that's just 1. So all these logs that look pretty complicated really just came down to a practice of what exponent of our base brought us there. Now, they don't always shake out like this, and I will show you how to plug these into your calculator as well. So let's practice converting each of these again from our exponential functions into our logarithmic functions. So I always ask myself, what is my base? Well, my base here is 2. So I know this is log base 2. Again, it's 2 that's being raised to an exponent. Well, log base 2 of my exponent, well, the thing that it equals is what we write down next. And then on the right-hand side, we write x for the exponent spot. So it's log base 2 of 16 is what equals x. Now we're looking at part B, where we have 10 to the minus 3. And with this one, we have our base is 10. And our exponent is minus 3. On the right-hand side of the equal sign, we have the 0.001. So log base 10 of whatever is in my equals, 0.001, equals the exponent minus 3. With the next one, I have e to the t equals 70. So my base is e, log base e. And we're going to learn a different way that we typically write log base e, since e is a very common exponential function that we deal with. So of course, log base e of 70 for the right-hand side of our equal sign equals our exponent t. So that is how each of these get written down, going from our exponential functions to our logarithms. These are all equivalent statements, essentially. All right, now let's do the other direction. If I'm given a base, let's rewrite it with an exponential. So here I have log base 2 of 32. So my base is 2. My exponent is whatever the log equals, which here is 5, and that equals 32. Now, I didn't actually calculate anything here. I do know that 2 to the 5 is 32, but I just picked all of this up from placeholders. So I have log base 2 of 32 equals 5. That tells me my base is 2, my exponent is 5, and the whole thing equals 32. With the next one, my base is a, my exponent is 8, and this all equals q. Again, just based off of where everything's sitting. With the last one, my base is t, my exponent is x, and all of this equals m. So we always want to keep that identity in mind. We can always go back and forth, basically just based off placeholders. Log base a of x equals y means x equals a to the y. And we just have to get used to going back and forth. Now, a couple of things that are important to note. If I ever have log base a of 1 and that equals 0. See, if I say a to the 0, applying all our rules, well, we know that equals 1, which means it doesn't matter what my base is, the log of 1 is always 0, because anything to the 0 power gives me 1. Now, if I have log base a of a, well, here I'm asking myself if I have a base of a and an exponent of 1, and when does this equal a? Well, of course, a to the 1 is always a to the 1. So in general, if I'm taking my base here and I have the same value here, it's always going to equal 1. Lastly, I just want you to note that the log base a of 0 does not exist. There's nowhere where I could write a to the something equals 0. I can't raise a number to an exponent and get 0, right? So I cannot ever have log base a of 0. We just say it does not exist. The same is true about negative numbers as well. I can never have a to some power equaling a negative number. This can't ever happen. Okay? Now, by default, like I said before, the log function on your calculator is going to be 10. And so if you want to actually change the base, you want to use this log base. And what you're going to go to is you're going to see math, and then you're going to see log base with an open parenthesis. You do have to scroll down a little bit to find it, but you'll be able to actually plug in what the base is there. So let's do that with these examples where it's a little bit trickier to actually figure out the decimals. So here we would be log base 10. So 10 to the what gives me 645,778. Well, let's go to our calculator and see what it is. See, I have log, and I can just use my standard log button here. It's log base 10 of 645,778. That's log base 10. Well, that's 5.810. So we write that down. Our question mark or our log equals 5.810. Great. Now we want to know what is log base 10 of this 0.0000239. So 10 to the something equals this 0.123. 4 zeros, 239. Let's check what that is. Going back to the calculator, and again here we can use our standard log, and it's 0.0000239, and that is negative 4.621. Back to our slides. Our question mark or our log equals negative 4.622. I did not remember that at all. Negative 4.622. See, the output of a log can be negative, right? Because 10 to a negative exponent makes sense on how we got such a small decimal here. Now, I already said we can't plug negative numbers into a log, and that's still going to be true, and I want to show you what happens on your calculator when you try. So now we're going to be looking at log base 10 of negative 3, and you're going to note 10 to, does anything give us negative 3? Should be no. So looking at our calculator here, if I do log of negative 3, enter, see it gives me an error. It knows it's not true, that it must be a real number. So I can either hit enter for quit, or I can go down to go to, and it'll bring me back to where I was in case I want to fix it for myself. So that's what happens. Your calculator knows you can't do this, and it will give you an error, and that was correct. So now, going back, no, this does not exist. So I like to write DNE for does not exist. Okay, now we'll see a couple examples where the log bases actually change. Log base 5 of 600. So 5 to some power gives us 600. And what power is going to do it? Well, let's go see on our calculator. And I'm looking at, I want to do a log base 5. So here I can't just use my standard log because that's log base 10. But if I go to math and I go down, I can find log base. So it's almost 11th in the list, I suppose. But if I hit enter, you can see now it's letting me type something for the base. So log base 5 of 600, enter, 3.975. So let's go ahead and write that down. This equals 3.975. And every time I write question mark equals, but it's really log base 5 of 600 equals 3.975, right? So I like to rewrite it to think about, okay, my base to what number gives me what I'm looking for, but in reality, to properly write it down, we want to say log base 5 of 600 equals 3.975. Let's do one more, log base 7 of 0.0049. So I go back to math and I go down to my log base 7 of 0.0045. That's negative 2.777. All right. Equals negative 2.777. So we can use our calculators on these, and even in that first set of them, we certainly could have done it as well. It's always good to do that to check our work anyways. Now, when we have a base of e, we start to call these natural logarithms, and we actually write it ln instead of log base e. So anytime you see ln of x, it's really just a simple way of writing log base e. Remember, e is that special number, the 2.71 that we learned last week, and we will see it come up a lot in different population dynamics. It has a ton of different applications out in the real world. So its log is a very special case that we try to pay attention to. And then, of course, with any natural log or any log in general, the log of 1 is always 0, and the natural log of e is, of course, just 1, since if we do log base e of e, we, of course, get 1. Whenever the base and what's in parentheses match, we always get 1. So let's practice working with natural log. A lot of these same things are going to apply. We'll see some different values here. So first one being natural log of 645,778. We go back to our calculator and we can type natural log of 645,778. You can see we have a natural log button directly on our calculator. This is 13.38. The next one, I won't jar you around and switch you back, but the next one asks for the natural log of 0.0000239. So we'll do that next. Natural log 0.0000239. And that, of course, is negative 10.64. Negative 10.64. All right, the next one asks for natural log of negative 5, which of course gives me an error. I cannot take the log of a negative number. So that was expected. The next one we're asked for are a couple that we can do by hand. So we will go back to the slides now. Here we are. This one, of course, does not exist. Natural log of e, we've already seen that before. This is log base e of e. That, of course, is 1. And the natural log of 1, of course, is 0. Now, looking at each of these, we actually want to convert them into exponentials or logarithms. So we're given 3 logarithms. We want to convert to exponentials. We're given 3 exponentials to convert to logarithms. So log base e of 6 is 1.7918. Here my base is e. So it's e to the, my exponent is what this equals, 1.7918. And that equals 6. Now again, I asked myself, for part B, I have natural log 7.3389. With this one, my base again is e. My exponent is what it equals to. And this, of course, equals what we're taking the log of, 7.389. With the next one, of course, we know this is true, a true identity, but we still want to write it. E to the exponent 0 equals 1. You do have several questions like this on your homework going back and forth between the natural log statements and the E statements. So it's important to make sure we know how to do this. All right, now going the other direction, I have e to the 3 equals 20.0855. Well, that means that the natural log of 20.0855 equals 3. Right? It always equals my exponent. Now, again, ln of 1.6487 equals my exponent 1/2. And lastly, ln of 0.3679 equals my exponent of -1. So there we've gone back and forth between the two. All of these are equivalent statements. Whether or not you picked it up on this side or this side, they mean the same thing. Feel free to use your calculator to check all that as well. All right, well, let's say that you have one base and you want to move to a different base. Well, we actually have a formula for that. So for any logarithmic bases a and b and a positive number m, the log base b of m is the same thing as the log base a of m divided by the log base a of b. So notice we went from a base b to a base a, and all we have to divide by is the log base a of the letter b itself. So let's practice that, and I have the formula at the top here for you. We want to change the base formula. So find the following logarithms using common logarithms and change of base formula. Common logarithms means using either 10 as a base or ln as your base. And so for this problem, we're going to use base 10. So looking at log base 5 of 8, we're going to use our little b is 5, our m value is 8, and our a value is 10. So to do a change of base formula, we then have log base 5 of 8 equals log base 10, which we don't typically write, of 8 divided by log base 10 of 5. And our practice for now is just to work on using this change of base formula, so I'm okay with you leaving it like that for now. Now with the other one, we have log base 100 of 60, and so our little b here is 100. Our m value is 60, and our a, again, is 10. Therefore, we have the log base 100 of 60 equals log base 10 of 60 divided by log base 10 of 100. Now, log base 10 of 100, 10 to the what gives us 100? Well, that's just 2. So this is really, well, I won't write 1/2, we'll write log base 10 of 60 divided by 2, which I could write as 1/2 log base 10 of 60. So we could simplify that one a little bit further. Again, just noticing that log base 10 of 100 equals 2. Now, looking at the last one, log base 7 of 16, we're going to do the opposite direction. So here we see our little a equals 7, our m equals 16, and our b equals 2. Therefore, this is equivalent to log base b of 16, which log base 2 of 16, 2 to the what power gives me 16? Well, 2 to the 4 gives me 16. Therefore, that whole thing simplifies down to 4. All right, so moving on. Given this graph, ln of 3 minus x, describe the transformations of the graph y equals ln of x. Also give the domain and the vertical asymptote. Now, this is ln of 3 minus x, and it is intended to be like that with the parentheses. That would be specified typically on an exam or something else. So we are going to graph this. We'll use our graphing calculator, and we're going to describe the transformations first. So in part B, what happened to natural log of x to give us natural log of 3 minus x? Well, we have done a horizontal shift because you see we have a plus 3 inside of the natural log. So we know we've done a horizontal shift left 3 units. We also have a minus x, so we know we have reflected over the y-axis, and I know it's the y-axis because every positive x became a negative x. So that flips it over the y-axis. Then right off the graph, we should be able to pick up the domain and the vertical asymptote. So let's take a look at our graph. Back to the calculator. Now, y equals natural log 3 minus x. Enter. What does that graph look like? Well, here it sits. So you see that it kind of starts off at 3 and it shoots up and left from there. So our domain is going to be from negative infinity up to 3. And we don't want to include 3, but we'll see that here in a moment. And we're also going to have a vertical asymptote at 3. See, it needs to level off and end right at 3, where we see it ending. Back to the slides now. So we saw the graph of it, and then the domain. Well, we saw that it was from negative infinity to 3, and see, we get that because we know 3 minus x must be positive, right? We can't plug a negative or a 0 into our function. Therefore, we know what we're plugging in, 3 minus x must be positive. So we can solve this by adding x to the left-hand side, and we know we get 3 is greater than x, or how I like to look at it is x less than 3, which of course is negative infinity to 3 with parentheses. And that is our true domain with the vertical asymptote at x equals 3. Now, we want to see an application as well. A study by psychologists Bornstein and Bernstein, it was found that the average walking speed in feet per second of a person living in a city of population P in the thousands is given by this function. So we have a 0.37 natural log of P plus 0.05. Now, we want to find if the population, like in Billings, Montana, is 106,954, find the average walking speed of that town. Then we're going to look at the average walking speed of Chicago with 2.7 million people. We're going to graph the function. Then we're going to see if we can't figure out when the average walking speed is 2 feet per second, what size population do we need? So let's work on each of these. First off, we want to find when P equals 106,954. See, the problem was given in terms of the thousands, right? So if I go back, a person living in a city of population P in thousands, which means I don't want to plug in 106,000. I want to plug in 106.954. Similarly, for part B, we're not going to plug in 2.7 million. We'll plug in 2,714. Technically, this would be 0.856 as well. So let's go to our function, our calculator, and see what these values are. We're going to be plugging in W of 106.954, which is 0.37 ln 106.954 plus 0.05. Alrighty. Let's get the calculator pulled up. Here we are. Clear it out. And we had 0.37 times natural log of 106.954, I believe, plus 0.05. Well, that's 1.7787. So 1.779. I'll write that down. And then the next one is 2,714. We will do the same thing there. So I don't know if you knew this about your calculator, but you can actually hit second enter to retype what you had before. So I'll go back and we'll clear out these values. And I'm going to do 2714.856. 0.86, close enough. 2.9754 is what we get. So I'll take you back to the slides now. Here we are. And I wrote down those values already. So that is what we get for these two values. Now let's go and look at the graph of this thing with a specific viewing window. And then we're going to see if we can't figure out when the walking speed is 2.0 feet per second. And here we are. Y equals 0.37 times natural log of x plus 0.05. And we graph. And let's look at our viewing window is going to be 0 to 600 and 0 to 4. So let's do that next. Window 0, 600, 0 to 4. And we'll get a really good idea of what's going on. And the scale here, I missed it. So the scale, if we're going from 0 to 600 on my x-axis, I probably want to count by 50s. Y-min, I said 0 to 4, and the scale of 1 is fine. We look at this graph. Here we go. We can see it a little bit more clearly now. This is what it looks like in this window. Now, we want to find when the walking speed is exactly 2, so I can go back to my y equals and type in 2. And if we look at that, where they intersect is exactly where our function hits 2 feet per second as our walking speed. And so I can calculate the intersection if I go down to intersect. And it says, hey, what's the first curve? It already picked it up, so I just hit enter. What's the second curve? I just have to hit enter. I don't need to guess. We hit enter one more time. And the intersection is 194.468. And that is the population of the city that we need. So 194,468. Really, if I want to properly round, 469. That would be the answer to that next question. So, moving on. I suppose I'll write down the answer. We already saw the graph. That was 194,469 people to get a walking speed of about 2 feet per second. Now, moving on, we actually are switching into section 5.4 here. We have a few rules for working with logarithms. Remember, logarithms are really the exponents that we have on our exponential functions. They kind of pick up what is that exponent. They help us solve for that exponent. So we actually get a lot of the same rules that we get out of our exponent rules. Namely, we have first the product rule, where if I have log base a of a times b, well, that's the same thing as log base a of a plus log base a of b. Notice I must have the same base throughout, but essentially I can turn multiplication into addition, but I will have log base a of a and log base a of b. So to see an example of this, I have log base 2 of p cubed and log base 2 of q, and this becomes log base 2 of p cubed times q. I go from having 2 log statements to just 1 log statement with multiplication in between. Now for the next row, we have something similar for quotients. I can have log base a of a over b, which is log base a of a minus log base a of b. So now I have subtraction in between them. So let's see this one in action. If we have log base t of 8 over w, well, that's going to be the same as log base t of 8 minus log base t of w. And that's it. We have just used that second rule. Now, just to see that rule going back the other direction, here's what we can get. We have log base b of 64 minus log base b of 16. Well, that's the same as log base b of 64 over 16, which of course is just log base b of 4. And that's it. That's how we simplify that one. Lastly, we have a power rule, where for any positive number a with a base a, lowercase a for our logarithm, and any real number p, we can go from having log of a to the p like this to now p log base a of a. So essentially I can take that exponent off the a and I can move it to the very front. And it's totally okay for me to do that. So let's practice that here. If I have log base a of 11 to the minus 3, well, that's the same thing as minus 3 log a of 11, just like that. Now, if I have log base a of 7, of the 4th root of 7, well, that's log base a. We'll rewrite it first as 7 to the 1 over 4, which now we can see clearly that the exponent can then drop to the front, and we have log a of 7. Now, lastly, we see we have natural log of x to the 6, which of course is 6 ln of x. So there's that rule. Now, typically you're actually going to see these rules combined. We're going to have to use multiple at once. And I like to just kind of start big and drill down inwards. So the biggest operation I see here is that division bar. So we start there. Let's use our quotient rule. Log a x squared y to the 5 minus log a z to the 4. Now that's the same thing. Let's do z to the 4 like that. Now I can break up my x times y. So I have log a x squared plus log a y to the 5th minus log z to the 4. Apologize for getting tiny on the corner there. Let's rewrite this one more time now. We can bring the exponents to the very front. So this becomes 2 log a of x plus 5 log a of y minus log a of z. Oh, I lost my 4. That's what I get for writing tiny in the corner. See, I have a 4 log a of z. That 4 drops to the front. So that's the fully simplified version of this here. I don't know if I'd actually call it simplified. It's the expanded version of the logarithms here. Let's do that again for part B. Now we have a third root on top of everything. So that, to me, is this overarching operation that's happening. So let's handle that one first. It's the biggest operation happening. So this, of course, is the same as log a of a squared b over c to the 5th to the 1/3. Right? Taking the cube root of something is the same as raising it to the 1/3. Now that 1/3 can drop to the front, log of a squared b over c to the 5th. And I lost my base a there, log base a. All right, so we did one of these now. So now let's do another one. I think the next biggest operation yelling at me is the quotient. We have a fraction bar there. Let's handle that next. That becomes 1/3 log a squared b minus log a c to the 5. And that 1/3 needs to be distributed to both terms, right? That 1/3 was on the exponent for all the terms. So we want to have parentheses here. Now going one more step, we have 1/3 log a of, breaking up the a and b, a squared plus log a of b minus log a of c to the 5. So we've broken up the multiplication between a squared and b. Let's keep going. We now have 1/3 log a of, 2 log a of a, plus, there's no exponent on the b, so that's just log a of b, minus 5 log a of c. And the last thing that we can do, though I am out a bit of room, this guy right here can be simplified to 1. This log base a of a is just 1, so that first term is just 2 plus log a of b minus 5 log a of c. Let's go ahead and write that out. I want to make sure you have really good complete notes, so I am going to take it over here to the left, and we get 1/3 2 plus log a of b minus 5 log a of c. There we go. So that is our fully expanded function of this logarithm. It was a lot of work just to get down to a single line. Now let's do this again, only we're actually going to do this in the opposite direction. Try to bring things back to a single logarithm. So if I have 5 log sub b, log base b of x minus log base b of y plus 1/4 log base b of z. Alrighty, so let's take care of the exponents first. This is the same as log b of x to the 5 minus log b of y plus log b of z to the 1/4. Just like that. Now the other thing I like to do is move that minus term to the end. Log b of x to the 5 plus log b of z to the 1/4 minus log b of y. See, when I have it on the end there, then I can clearly identify, oh, that's going to be my quotient, and I'm going to have a product first. So let's handle that product. The addition turns into a product, x to the 5, z to the 1/4, minus log b of y. And now we just do our quotient rule, log b of x to the 5, z to the 1/4 divided by y. And that is it. That is it for this question. So we were able to simplify these multiple logs with all these different numbers down to a single log question. Let's do this again. Now we have natural logs. We have natural log of x minus 2, natural log of x minus 5, plus natural log of x plus 5. So using our rules, I'm going to handle what's in parentheses first. This becomes ln of x minus 2. Now, with the addition, I'm going to turn that into multiplication. ln x minus 5, x plus 5. And all of that is inside my natural log here. Let me make my parentheses a little bit more clear here. I don't really need it in front of the beginning there, so I'm going to redo this and write ln x minus 5, x plus 5. Like that. That way we can really see the x minus 5 and x plus 5 are in the parentheses in the natural log. We can FOIL that out. We will get ln of x minus 2 ln x squared minus 25. Right? That's our square minus the square case for the factoring. We know it'll simply FOIL to x squared minus 25. Okay, so now we have the 2 in front of the natural log. We got to handle that before we can use our quotient rule between the x and the x squared minus 25. So that's the next operation we got to handle. Let's move that 2 out of the way. We have ln x squared minus 25 squared, like that. Last step, ln x over x squared minus 25 quantity squared. That's what this whole thing simplifies down to. Notice the square is just on the bottom because that 2 went into the exponent of the x squared minus 25. All right, the x on top is not squared. The x on top had no exponents, so it just stayed. So in summary, here are your log rules, and these are the exponent rules that they should remind you of. So when we do the log of a times b, that's the same thing as log of a plus log of b. Well, that really comes from the rule where we can add exponents. X to the m times x to the n is x to the m plus n. Similarly, for the other two rules, they correspond to these exponent rules. So it's really good to have all 6 of these in your back pocket. I will list all 6 of these on the final exam for you in that little formulas box to help you out. So the last thing I want to mention for now, what I believe is the last thing, are these quick identities. So notice if I have log base a of a to the x, it simplifies down to x. And if I take some a and I raise it to the log base a of x, that also simplifies to x. So essentially, this proves that log base a of x and a to the x are inverses. So that is y equals log base a of x and y equals a to the x are inverses. If you plug one into the other one, it simplifies all the way down to x. So we're going to see some of that here. If I have log base a of a to the 8, that of course simplifies to just 8. If you really want to write it the long way, it would be a to what power gives me a to the 8. So naturally, 8 gives me a to the 8. Now with the next one, ln of e to the minus t, is just minus t. With the next one, if I have 4 to the log base 4 of 3k, the 4 and the log base 4 cancel, we get 3k. And if I have e to the natural log of 5, that simplifies to just 5. So these are true inverses. Essentially, if you see that your bases match, so in the first one we had a as our base, in the second one we have e as our base, in the third one we have 4 as our base, and the last one we have e again as our base. When that happens, you know you can just take whatever's in the parentheses or in the exponent. So in the first case, we just took the 8. In the second, we took the negative t. In the third, we take the 3k. And in the fourth, we took the 5. That's what happens in general with these. So as always, if you have any questions, please reach out.